If you haven't done so yet, make sure you pause the video and attempt to answer this question on your own first before listening on. And it turned out that this question was rather difficult to solve because the authors actually made a mistake in how they presented the numbers in the table. So let's try to explain that. It turns out that if you use the numbers as they are shown in the original question, as you see here on the screen, the problem would actually turn out to be unsolvable. And so I think what the authors meant to say is that these numbers right here were actually the values for the potential difference, or the volts. And then these numbers here were supposed to be the currents that were measured. So we just have to shift those numbers over, and then we're going to be able to more thoroughly solve this question. And the reason this will all make sense now is because we're going to be able to calculate the three resistances of the table, because we know from Ohm's law that the potential difference is equal to current multiplied by resistance. So if we take that equation and divide both sides of it by the current I, the current would cancel out on the right hand side, and we would have delta V over I is equal to the resistance. So for example, for this missing value of the resistance right here in the table, we could take the delta V and divide it by the current right here, and that's going to give us the resistance. So let's pick up our calculator and divide the 5.22 by the 0.5. And when we do that, we get 10.4 ohms. And we're going to do a similar calculation to get the other resistances here and here. So we'll divide delta V by the current. And so we have now successfully determined the resistance for each of the three situations in the experiment. We next need to figure out the resistivity. And to determine that, we look at this equation that tells us that resistance is equal to resistivity times length divided by the area. And it turns out that we can solve this equation for the resistivity. And to do that, we can multiply both sides of the equation by the area A, so that it cancels out on the right-hand side. And then we'll divide both sides by the length L, so it cancels out on the right. So we can see that the resistivity, which is symbolized by this Greek letter rho, is equal to the area times the resistance divided by the length. So for example, for this entry right here, we're going to take the area, which was given to us in the question, right up here. We'll multiply it by the resistance, and then divide by the length. So we've come over here and shown that setup. And if you carefully punch that into your calculator, you should get about 1.41 times 10 to the minus 6. And the unit will be ohm meters, because the meters in the denominator here will cancel with one of the 2 meters up here. So you'll be left with ohm meters as the unit. So you're going to do the same thing to get the other resistivities. So for the second one, we would take the same cross-sectional area. We'll multiply it by the resistance, which was 21.1, and then divide it by the length for that part of the experiment, which was 1.028. And when you work that out, you're going to get about 1.5 times 10 to the minus 6. And then we'll do the last setup for the third row of the experiment. And you once again get 1.50 times 10 to the minus 6 ohm meters. So now we just have to find the average value of the resistivities, and there are 3 of them. So of course, to find the average resistivity, we just have to add all 3 of them up and then divide by 3. So there is the setup, and when we work that out, we get 1.47 times 10 to the minus 6 ohm meters. So this is the value for the average resistivity and the correct answer to the first part of the question. We then simply have to compare this value with the given value of table 17.1. And so here is a portion of that table. We can see that for nichrome, the resistivity is 150 times 10 to the minus 8th. Notice that you can rewrite that in terms of a power of 10 to the negative 6. And the trick for doing that is to take this decimal point and move it over 2 places to the left, so it becomes 1.50. And if you move your decimal place to the left by 2 places, that means you have to add 2 to this exponent. So that'll become times 10 to the minus 6. And so now that we have them in the same basic form, we can basically do a percent difference. which can be calculated by taking the known value of 1.50 times 10 to the minus 6 and subtracting 1.47 times 10 to the minus 6, and then put that over the known value. Now you'll notice I'm omitting the times 10 to the minus 6 because if I entered it in right here, and here, and then in the bottom, they would actually all cancel out. So it's easier just to omit them all together. And then once we have that set up, we can multiply by 100 to convert it into a percent. So if we do that, we're going to get exactly 2%. And so what we can conclude is that the experimental value, this value right here, is 2% smaller than the stated value in the table.